So we'll continue with stereoscopic parallax. So parallax is defined as apparent displacement of the position of object with respect to a frame of reference due to shift in the point of observation. So you must have observed when you're moving and you're looking at the same object, it would seem as if the object is moving. So you can see in this picture that if you take a picture of the same object from a flying drone and the direction of the drone is fixed, so it's traveling in this line, which is called as line of flight. So it's traveling in a straight line, and you take two pictures of the same object at different time. So basically, the drone has moved a distance between the time that you took the first picture and the time you took the second picture. So it has moved a certain distance, and in the two pictures, it would seem as if the object is moving. So this apparent movement of the object is called as parallax. Now, this parallax is a function of its height. So that means how different the height of the object is, the more or less would be the movement in successive pictures. So this function or this property basically helps you in determining the height of the object because it's a function of the apparent movement on pictures. And it is also possible to compute x and y coordinates from parallax. So how you go ahead with this procedure is that first you ascertain the line of direction, and then you can take an arbitrary x and y axis, and on that x and y axis you can calculate the parallax, and then you can calculate the height of the object and the x and y coordinates. And for that you need to have overlapping photos. So in overlapping photos, the same object should be visible in the two photos, and the same reference should be visible. So if you've taken a certain xy coordinate at a certain origin, that should be visible in both the pictures. So this is how it's done, that in the same line of direction of the flight, two pictures are taken at different time, and the distance moved by the plane is noted. So a line is then uh, ruled through these two pictures, and it serves as the x-axis. And on 90 degrees, you can draw the y-axis, and the origin can be at the center. So the parallax would be that the x-coordinate of a point is scaled on each photograph with respect to the axis constructed, and the parallax is calculated from the expression x minus x1. So the coordinate of the picture of the point in the first picture minus the coordinates of the point in the second picture, and the signs have to be according to the origin. So it says that photographic coordinates x and x1 are measured on both the photographs. The photographic coordinate should be used with the relevant sign, and then parallax can be calculated. So with reference to the same origin, uh, whatever the signs may be for the x and for the x coordinates, because the object could be about the both axes, left or right, so the sign could be negative. So you take it with the whatever the sign there is, and you calculate the parallax. And the distance between the first picture, the point where the first picture is taken, it's shown by this point L over here, and the second picture is taken at the point L1, and this distance between the 2 points is called as air base, and it is denoted by B. Another thing is that the datum should be known, because in the previous questions we also saw that the height of the drone is from a certain datum, and whatever height of the object that you're calculating would be from the same datum. So that datum has to be defined beforehand. So these are the equations that we would be using. The first equation can be used to determine the height of the object. In this equation, you have capital H, which denotes the flying height of the drone from a datum. Small h denotes the height of the object from the same datum. B is the airbase, which means the distance between the point where the first picture is taken and the point where the second picture is taken. Small f is the focal length, and you divide it by p, which is the parallax. And for the second equation, is this gives you basically the actual ground coordinates, capital X, for the object, and in the equation you have b, the airbase, divided by the parallax of the point multiplied by the x coordinates, so the coordinates on the first picture. And similarly you can calculate the y coordinate. So why it's important to calculate the ground coordinates, because once you have the ground coordinates x and y for different points, you can calculate the distances between them. So over here we have a question which says that the length of line AB and elevations of points A and B whose images appear on two overlapping vertical photographs are needed. The flying height above Datum was 4050 feet and the air base was 2410 feet. This means the capital H is 4050 and the air base B is 2410 feet. The camera had a 6-inch focal length, so that means focal length small f is 6 inches, and the measured coordinates in inches on the left hand image are XA, XB, YA, YB, and on the right hand image are X1A and X1B. So basically, two pictures are taken, two overlapping pictures, and there are 2 points A and B. And what they ask you to find out is the length between AB, so ground length between AB, and they ask you to find out the height of the line AB. So that means you can calculate the height of the point A and the height of the point B. So for this, since we have 2 points, so both the points would have the different parallax because parallax is a function of the object height. So we would calculate one, the parallax for the point A, and second, the parallax for the point B. Once we have these two parallax values, we can calculate the heights of point A and the point B, and then we can calculate the ground coordinate x and y for point A and the ground coordinate x and y for the point B. Now, once we would have the ground coordinates xy for A and xy for B, you can calculate the distance between AB using the distance equation, which is x2 minus x1 squared plus y2 minus y1 squared under root. So that would give you the distance between the points AB. So the first thing to do is to find out the parallax for the point A and the parallax for the point B. So like we saw before, that parallax is basically x minus x1. So the x coordinate of point in first picture and the x coordinate of the same point in the second picture. So over here we are given for the point A, xa, which is the first coordinate, and we are given x1a, which is the x coordinate of the same point in the second picture. So parallax for A would be xa minus x1a. So the second point is denoting by x1a, and see that the sign remains the same in the equation and you get the parallax. Similarly, you can calculate the parallax for the point B in the same way. Now, once you have these, you can calculate the height of the point A and the point B using the equation that we saw on the previous slide. So from this equation, capital H was the height of the drone it's given, 4050 feet. Then you have minus the airbase 2410 it's given, focal length is given, and parallax for A we just calculated 4.35 inches. So you have to take care of the units in the equation, and you get the height of the point A as 726 feet and height of the point B as 954 feet. So now that we have heights for the point A and B, now we need to calculate the x and y coordinates, the ground coordinates for A and B separately. So for that, we have the equation for x coordinate of the point A. The equation is air base divided by parallax for A multiplied by the x coordinates of A in the first picture. So replacing the values in the equation, we calculate xa. Similarly, for B, the same equation. Similarly, we can apply the equation for y coordinates for both the point A and the point B. Now, for the y coordinate, again, we would be using the same parallax value because parallax equation is a function of the height, and you can calculate x and y coordinates using the same parallax. Parallax आपके पास एक ही उससे आएगा from the same equation, which is the coordinates in reference to the direction of flight. So since we've called it as x, so we're using x to calculate parallax. So now that we have x and y coordinates with the relevant signs, we can replace it in this equation of AB over here and calculate the distance AB. So this is how parallax can help you in calculating the height of objects as well and the distances as well. So vertical photograph can be useful in both calculating the elevations and the ground distances. So if you want to carry out photographic surveying, what sort of information do you need to plan? How are you going to proceed with it? So in planning, what you need to ascertain is that what should be the flying height of the drone, um, what should be the route on which it should fly, because once you want to survey a large area, you need to predetermine what should be the route of the drone. So for that, you need to see that what are the boundaries of the area to be covered, what is the required scale of photography and camera focal length format size, because that would ascertain the limitations on the flying height. End lap and side lap. So we'll talk about end lap and side lap. They're very important. We'll talk about it in a second. So once these elements are fixed, then you can actually decide on what route the plane would take. Now talking about side lap and end lap, so when you actually ascertain or you want to determine the uh, when you want to carry out the photographic surveying over a large area, so you need to ascertain what should be the route on which you want to fly your drone. So that depends on how much side lap and end lap should be there in each photograph. So side lap and end lap means that when your plane is flying in a direction, so when your plane is flying in a certain direction, so it would go from here, take a turn, and then return back. Now, this area is overlapped between two photographs taken sideways. So over here, you can see in this picture, when it's flying in the same direction, in parallel directions, one way or the other, this is the area covered in one photograph, and this is the area covered in the second photograph. And this over here is the overlap between the two photographs. Because later on, you're going to stitch these pictures together, and the software would need to know a certain same area between two photographs so that it can easily stitch them together and you get a total map of the whole area. So that is why you need to have side laps and end laps. So this is the lap or the overlap which is there when the plane is flying in parallel directions. Similarly, end lap is there when you're flying in the same direction and you take successive photographs. What should be the distance or what should be the area which is there in both the photographs which is overlapping? And we use this same overlapping thing in parallax as well. So end lap is when your plane is flying in the same direction and it takes successive photographs. So what should be the distance at which it should take each photograph? And side lap is when it takes a turn and comes back and has a side overlap between successive pictures. So according to general convention, it says that the the strips or flight lines generally have a side lap of about 30%. So at least 30% of the area is overlapping, and end lap of about 60 plus minus 5%. So there should be more end lap and lesser are the instructions for the side lap. But these values depend on different conditions such as your the topography as well, and it depends on the type of drone and the focal length and different factors. But these are just some reference values. So once you decide on what should be the side lap and end lap, then you can plan this whole scheme. So you have a total area which is 15 miles multiplied by 10 miles. So you have huge area. And then you have to ascertain that what should be the distance between uh, the parallel turns of the airplane. And over here, they're saying there should be 6,600. And obviously, it comes out from the total area, which is covered in one photograph, which depends on the focal length and the flying height of the plane. And once you have that total area, then you can see that by taking a side lap of, let's say, 30%, how much should be this distance at which it should take the turn. So all of these things are planned and then they are set in the navigation, and then automatically the drone flies and takes successive pictures at the instances that you have actually told it to. So the information which is calculated in flight planning includes flying height above mean sea level because this would control the scale of the photograph, distance between exposures, this would ascertain the end lap, number of photographs per flight line, again this would ascertain the end lap that you have, distance between flight lines, this would ascertain the or take care of the side lap, number of flight lines, again that this depends how much accuracy do you want, and total number of photographs. So then we have ground control for photogrammetry. So almost all phases of photogrammetry depend on ground control. Some points of known elevations and identifiable points on the ground. So we use the same technique in finding out the scale as well. So the ground control can be basic control such as traverse, triangulation, trilateration. And basically what you can do is you can ascertain the accuracy of the scale that you've calculated or the distances you have calculated. You can go to the ground and do ground truthing. That means you can see if the distances are same as the ones you've calculated from the picture, and that will tell you how accurate your whole scheme of work is. Analytical photogrammetry means once you have taken the pictures, you put them in the software and then you take out all the relevant information that you want. So you can calculate the photo coordinates and the ground. From those, you can calculate the ground coordinates and all sort of data that you want to take out of those pictures. So the accuracies that you can get from the whole photogrammetry procedure are about 1 over 10,000 to 1 over 15,000 of the flying height above ground. So that means the accuracy depends on the flying height. So more the flying height, then obviously the accuracies would decrease. So the lower is the height, the more would be the accuracy of whatever information you want to gather from the ground. Now comes the concept which is called as orthophotos. So like I told you that on a picture, scale plays a very big part and the points which are at different elevations have different scales. So orthophotos are the photos which have been geometrically corrected or orthorectified such that the scale of photograph is uniform and utilized in the same manner as a map. Because on a map, the scale is same throughout. Whatever information you take out from a map, whatever reading you take from a map, the scale would be same throughout. But it's not the same case in pictures because the scale depends on elevations. So using those elevations, if the elevations are known and the software is asked to construct a picture which has taken care of the scale, and so that you can apply the same scale to the entire picture. So that picture would be called as an orthophoto. So it is constructed by rectifying the image by using the pixels, and the output that you get is a picture like this. So if you look at this picture, you would see that there is distortion in this picture. And that distortion is basically because the picture has been rectified for scale. So it has been readjusted so that now this picture would act as a map. Every reading you take of this picture would have the same scale everywhere. So now basically it can be used as a map. So these are very useful. They have a variety of applications such as planning, engineering design, cadastral maps, tax mapping, GIS analysis, a lot of different functions that these pictures can perform. So you can see how in one picture you can see that the points are at different elevation, and in the other picture, which has been auto rectified, you can see how all the points seem to be at the same elevation. So once these pictures are corrected and stitched together, you get orthomosaic maps. So these consist of series of photos which have been rectified and then which have been combined together so that you get ortho rectified map which has taken care of the scale. So these are very useful in construction as well. You can see how the progress of a big project is going with time, and you can observe the progress by taking these pictures and prepare a progress report based on it. So, like I said, we have different softwares which can each quickly process these pictures and give you all the information that you need. You can do it manually as well if the work that needs to be done is not a lot. But if it is, then you can actually use different software for this. So we have different softwares which can be used, such as ESRI Drone to Map, which is basically input for ArcGIS software. And then we have another one by Autodesk. So we have different softwares which can be used to process these pictures and then make them usable to be used in GIS as well. Okay, lastly, let's talk about some errors which are expected or which can be a source of error in your whole calculations. So some sources of error are measuring instruments not standardized or calibrated. So this is a probably a big issue when you are using ground truthing. So whatever instrument you're using to calculate distances on ground, that has to be accurate, and the camera has to be standardized. The focal length has to be accurate as well. Inaccurate location of principal and corresponding principal points. So on the picture, you need to accurately determine what is the principal point or the center point of the picture. Failure to use camera calibration data. Again, this also deals with the errors that arise in the scale. Assumption of vertical exposures when photographs are actually tilted. So we began our discussion with talking about vertical and oblique photographs. And for this procedure to work, your picture has to be exactly vertical. If it's oblique, then obviously the scale errors would be there, and you have to make sure that your pictures are exactly vertical. Presumption of equal flying heights when they were unequal. So you have to make sure that the drone has to fly at the same elevation while taking successive pictures. If it changes its elevation, then obviously your scale and all the calculations would change. Incorrect orientation of photographs. So that's again, successive photographs have need to have side lap and end lap, and then they are stitched together to make a proper map. So if you have faulty orientation, this would be a problem in finding out parallax, and this would be a problem in building larger maps from these smaller photographs.